Today I'm going to present an EIST2018 project called Distributed Spacecraft with Heuristic Intelligence to Enable Logistical Decisions, DShield. I have been privileged to partner with several universities, including USC and Texas A&M, for this effort beyond NASA Ames Research Center. To summarize, DShield is a suite of scalable software tools that helps to schedule payload operations across a large constellation, which will have multiple payloads on every spacecraft and heterogeneous payloads across spacecraft. And the goal is to schedule observations and downlinks in this constellation to maximize science value for any selected use case, constrained by constraints like as a value function, spatio-temporal invariant value function. The snapshot is shown on the left. And we were able to show that with this onboard scheduler, we can observe 7% more flood magnitude than a ground-based scheduler. And either approach observes 98% better than constellations that just stare straight down and do not have agility. Next slide, please. So the concept of DShield is to extend this very preliminary framework to a higher fidelity approach to allow for multiple payloads on a spacecraft and heterogeneous payloads across the constellation, higher fidelity tools for scheduling and estimation of constraints, and apply to a much more complex scenario of soil moisture monitoring globally and to bring down the uncertainty estimate of soil moisture. So DShield has three components: the scheduler on the top, which at the heart of which lies the optimizer, which takes into account constraints from orbital mechanics, active control systems, power, data, instruments, ground module, and intersatellite comm. And it throws out the optimal schedule, that is, what ground point should a satellite be pointing to at a given instant of time, and what instrument should it be using during that time. The objective function of this optimizer is informed by the science simulator, which has components of a nature run and also data assimilation from not just measurements made by the test constellation, but also third-party sensors like Cygnus and SMAP. This whole technology box, scheduler for science simulator, is analyzed by the third part of DShield called the analyzer, which shows the sensitivity of performance as a function of various input parameters like constellation orbits, instrument specs, and other user requirements. This can either come from existing constellations or from design tools like TAT3, which has been previously funded by EIST. Next slide, please. So we want, like I said, we want to apply DShield to a use case for soil moisture monitoring, and for this purpose, we're using measurements from Soilscape, which is a ground sensor network, thanks to Professor Mugaddan's group in the University of Southern California. The goal is to add noise to these measurements to find the minimum acceptable sigma NEZ that a small satellite can measure and is useful to the soil moisture community. Find a representative constellation with 3 types of instruments, which I'm going to be talking about, and then use DShield to schedule the constellation to make multi-payload operations. And there's various aspects of the science simulator that we're going to be working on for the next 2 years of this project. Next slide. Since DShield is primarily a scheduler for a given constellation, the first step is to down-select certain representative constellations carrying combinations of L, C-band radars, radiometers, and reflectometers. And for this purpose, we're going to be using the VASR tool developed by Professor Selva in Texas A&M University, as well as an ESTO-funded TAT3 tool to come up with some constellations that lie on the Pareto front of science, utility, and cost. Next slide. So a few tech details on DShield in the next couple of minutes. There's several modules that we're increasing fidelity from, all of which will be available as standalone Python packages in a couple of years open source. So for example, the orbit and instrument module work in tandem to produce a set of observation opportunities and communication contact opportunities from left to right, and observation metrics from right to left from instrument to orbit. Next slide. The orbit module is a simple analytical dynamic model with just J2 perturbation, which is capable of providing coverage for any satellite and any orbit, given 2 approaches. One is the grid point method, so it tells you which places on Earth the satellite can see at any given instant of time. And also the pointing options method, that is, if the satellite were not to be pointing statically downward and in some other direction, what are the different points it could see? Next slide. The instrument package is very simple, considers observation geometry and instrument specifications for some standard instrument suites, provides metrics like range, incident angle, solar elevation angle for basic instruments, and other more complex metrics like SNR, NEDT, dynamic range for passive optical, sigma NEZ, incidence angle, and so on for the SAR instruments. Next slide. So we will also have a spacecraft sizing module. So for any of these instruments, we want to estimate how big the spacecraft will be. And more importantly, this module will also inform operational constraints for the planner to take into account which instruments can be used at what time and at what duty cycle. Next slide. So the work in progress is, since we just started this project a couple of months ago, the DShield optimizer is prototyped on a greedy path selection using dynamic programming, which has worked really well so far for simple use cases. But as we scale to more complex use cases, we're developing a modular path optimization approach that will guarantee real-time solutions as well as be scalable to scores of assets in terms of constellations and ground stations. There's a lot of work going on in maturing the attitude control module and the DTN-based communication module, and also building up the power and data modules to inform the optimizer. And lastly, there's the science simulator based on the OSSI approach for the soil moisture relevancy scenario. And once that sizing is complete, we want to use the science simulator and the instrument module to build a spatiotemporal value module that can inform the optimizer and the analyzer. So that's it from my side. Since we have just 20 seconds, happy to take them on chat as well.